In an atom, electrons are present in orbitals of differing energy levels, such as 1s, 2s, 2p, and so on. They represent the probability of finding electrons around an atom. This observation led scientists F. Hunt and R. S. Millikan to develop the molecular orbital theory, which postulates that electrons in a molecule similarly exist in different orbitals, giving the probability of their presence around a molecule. However, for atomic orbitals to combine and form molecular orbitals, they must have similar energy levels and symmetrical molecular axes. This means that even though 2px of one atom has energy equal to 2py of another atom, they won't combine as they don't have the same symmetry. The number of molecular orbitals formed is equal to the number of atomic orbitals in the atoms forming the bond. Electron distribution in molecular orbitals takes place as per the Aufbau principle and obeys Pauli's exclusion principle and Hund's rule. The electrons in an atom are influenced by only one nucleus, forming monocentric atomic orbitals. However, the electrons distributed in molecular orbitals are influenced by the nuclei of all the atoms forming the molecule, causing the formation of polycentric molecular orbitals. In an atom, the electrons present in the atomic orbitals are represented using the Schrödinger wave equation of wave mechanics by the wave function y, which gives the amplitude of the electron wave. However, the Schrödinger wave equation cannot be used for molecules, and hence a new method called the linear combination of atomic orbitals, LCAO, was developed. To understand this method, let's consider the hydrogen molecule made up of two hydrogen atoms, A and B. At ground state, each hydrogen atom has one electron in the 1s orbital. Let's represent their wave function as psi A and psi B. Now, there are two ways to add the wave functions. One is when these wave functions are in phase, either both plus or both minus. And the other is when the two wave functions are out of phase, one plus and the other minus. When the two electron waves are in phase, they form the bonding molecular orbitals. Here, the electron density is between the two nuclei. The electrons tend to hold the nuclei together, thus stabilizing the molecule. Therefore, we conclude that a bonding molecular orbital always possesses lower energy than either of the atomic orbitals that have combined to form it. When the two electron waves are out of phase, they form antibonding molecular orbitals. Here, the electron density between the two nuclei is reduced such that it is zero at the nodal plane. This leads to mutual repulsion of the electrons. as the energy of the mutual repulsion is more than the attraction between the electrons and the nuclei, the net orbital energy increases. Thus, the energy of the anti-bonding orbital is raised above the energy of the parent atomic orbitals that have combined, and the energy of the bonding orbital is lowered than the parent orbitals. However, the total energy of the two molecular orbitals remains the same as that of the two original atomic orbitals. As we have learnt, molecular orbitals are obtained by combining the atomic orbitals of the atoms in a molecule. For example, in the hydrogen molecule, each atom has one electron in its 1s orbitals. These two 1s orbitals come together to form two molecular orbitals. One of these two molecular orbitals is formed due to the constructive interference of the two 1s wave functions, and the other is formed due to the destructive interference of the two 1s wave functions. The molecular orbital formed due to constructive interference is called a bonding molecular orbital, as the electrons belonging to it are placed between the two nuclei. This stabilizes the molecule. The molecular orbital formed due to destructive interference is called an anti-bonding or sigma star molecular orbital, as the electrons belonging to it are placed away from the region between the two nuclei. This increases their energy, thus making the molecule less stable. Just as in atoms, electrons in a molecule too first occupy lower energy levels. Thus, we find that the two electrons of the hydrogen molecule first occupy the sigma bonding molecular orbital. This lowers the overall energy of the molecule compared to the isolated hydrogen atoms. Molecular orbitals not only help us determine the stability of molecules such as hydrogen, they also help us understand why certain molecules such as the helium diatomic molecule do not exist in nature. You see, helium atom has two electrons in its 1s orbital. When two helium atoms come together to form a molecule, the 4 electrons would be distributed across both sigma bonding and sigma star anti-bonding molecular orbitals. The energy of the sigma bonding molecular orbital will be low. However, the energy of the sigma star anti-bonding molecular orbital will be considerably higher. Thus, the overall energy of a helium diatomic molecule will be the same as that of two helium atoms. So, there will be nothing holding them together. Hence, the helium diatomic molecule does not exist. 4 molecules formed by atoms containing more than 2 electrons. We will only consider the molecular orbitals formed by their valence shell and not the ones formed by their core orbitals to understand their stability. Now let's study the molecular orbitals formed in an oxygen diatomic molecule. Oxygen has the atomic configuration 1s2, 2s2, 2px2, 2py1, 2pz1. When 2 oxygen atoms come together, their 1s2 atomic orbitals combine to form 2 molecular orbitals. Their electrons are concentrated along the bond axis. Hence, they are called sigma 1s bonding and sigma star 1s anti-bonding molecular orbitals. The two 2s orbitals combine to form sigma 2s bonding and sigma star 2s anti-bonding molecular orbitals. Two 2pz orbitals too combine head-on to form sigma 2p bonding and sigma star 2p anti-bonding molecular orbitals. However, the two 2px and 2py orbitals combine sideways to form a p orbital shaped bond with the electrons concentrated either above or below the bond axis. Hence, these molecular orbitals are called pi orbitals. The two px atomic orbitals combine to form pi x bonding and pi star x antibonding molecular orbitals, whereas the two py atomic orbitals combine to form pi y bonding and pi star y antibonding molecular orbitals. As the energies of the 2px and 2py atomic orbitals are the same, the energies of pi x bonding, pi y bonding molecular orbitals and pi x star antibonding, pi y star antibonding molecular orbitals are the same. Thus, the interaction between the valence shells of two oxygen atoms leads to the formation of 8 molecular orbitals: sigma 2s, sigma star 2s, sigma 2p, sigma star 2p, pi x, pi y, pi star x and pi star y. Due to the difference between 2s and 2p atomic orbitals, the resultant molecular orbitals sigma 2s and sigma star 2s lie below the other 6 orbitals. Due to the head-on bonding between 2pz atomic orbitals, the interaction between them is stronger than the 2px and 2py orbitals. As a result, the sigma 2p orbital lies below the pi x and pi y orbitals, and the sigma star 2p orbital lies above the pi star x and pi star y orbitals. While this sequence of molecular orbitals is accurate for molecules such as oxygen and fluorine, but not for other elements such as boron, carbon and nitrogen, the molecular orbital's energy sequence is slightly different. This is because of the interaction between the electrons of the 2s atomic orbitals of one atom with the electrons of the 2pz atomic orbitals of another atom due to their relatively similar energy levels. In these molecules, the energy level sequence is sigma 2s, followed by sigma star 2s, followed by pi x and pi y that are at the same energy levels, followed by sigma 2p, followed by pi star x, pi star y, and finally sigma star 2p. As we know, the number of bonds between a pair of atoms is called the bond order. In terms of molecular orbitals, to calculate the bond order, we assume that 2 electrons in a bonding molecular orbital form one bond, and that 2 electrons in antibonding molecular orbitals cancel the effect of one bond. Thus, we can calculate the bond order in an oxygen molecule using the formula bond order is equal to number of electrons in the bonding molecular orbitals minus number of electrons in the antibonding molecular orbitals divided by 2. Now, in oxygen, the number of electrons in the bonding orbitals is 8, and the number of electrons in the anti-bonding orbitals is 4. So, adding these values to the equation, we get the bond order as 2. As we know, when electrons in an atom or molecule are paired, as in nitrogen, they form a dimagnetic atom or molecule. And when the electrons in an atom or molecule are not paired, as in oxygen, they form a paramagnetic atom or molecule. In this way, the molecular orbital model helps us understand the structure and properties of molecules. Let us start with the hydrogen molecule, which is formed by the combination of two hydrogen atoms. You know that a hydrogen atom has just one electron, and it is placed in the 1s orbital. So, a hydrogen molecule will have two electrons that are present in the sigma 1s molecular orbital. The electronic configuration of a hydrogen molecule is sigma 1s2. Let us calculate the bond order of hydrogen molecule. As the number of electrons present in the bonding orbital is 2, and as no electrons are present in antibonding orbitals, the bond order is equal to 2 minus 0 divided by 2, which is equal to 1. This shows that there exists a single covalent bond between two hydrogen atoms. The hydrogen molecule is dimagnetic in nature, as no unpaired electrons are present in its molecular orbitals. Now let us discuss the bonding in a helium molecule. A helium atom has two electrons in its 1s orbital. Hence, the number of electrons in a helium molecule is equal to 4. These electrons occupy the sigma 1s and sigma star 1s molecular orbitals. Hence, the electronic configuration of a helium molecule is sigma 1s2, sigma star 1s2. Now, from the electronic configuration of helium, we can easily derive the bond order of the molecule. As the number of electrons present in both the bonding orbitals and anti-bonding orbitals is 2, the bond order is equal to 2 minus 2 divided by 2, which is equal to 0. This proves that a helium molecule is unstable and therefore does not exist. Similarly, beryllium molecule with an electronic configuration of sigma 1s2, sigma star 1s2, sigma 2s2, sigma star 2s2, and a bond order of 0 is considered to be non-existent. Now let's see the bonding in a lithium molecule. A lithium atom has an electronic configuration of 1s2 2s1. Thus, there are 6 electrons in a lithium molecule. The electronic configuration of a lithium molecule is sigma 1s2, sigma star 1s2, sigma 2s2. This configuration is also written as Kk sigma 2s2, where Kk represents the closed K-shell structure sigma 1s2, sigma star 1s2. As lithium has 4 electrons in its bonding molecular orbital and 2 electrons in the anti-bonding molecular orbital, the bond order of lithium is calculated to be half of 4 minus 2, which is equal to 1. From the bond order, it is clear that lithium is a stable molecule, and as no unpaired electron is present in its molecular orbitals, it is dimagnetic in nature. This dimagnetic lithium molecule is found to exist in the vapor state. Now, we'll see the bonding in another diatomic molecule, carbon. An atom of carbon has an electronic configuration of 1s2, 2s2, 2p2, which makes a total of 12 electrons in a carbon molecule. The electronic configuration of a carbon molecule is sigma 1s2, sigma star 1s2, sigma 2s2, sigma star 2s2, pi 2px2, pi 2py2, which can also be written as kk sigma 2s2, sigma star 2s2, pi 2px2, pi 2py2. The bond order of carbon can therefore be calculated as half of 8 minus 4, which equals to 2. In a carbon molecule, the two atoms have a double bond between them. Both the bonds are pi bonds due to the presence of 4 electrons in 2 pi molecular orbitals. A carbon molecule is dimagnetic as no unpaired electron is present in its molecular orbitals. It is found to exist in the vapor phase. Now let's look at the bonding in an oxygen molecule. Two oxygen atoms combine to form an oxygen molecule. The electronic configuration of an atom of oxygen is 1s2, 2s2, 2p4, and hence there are 16 electrons in a molecule of oxygen. The electronic configuration of oxygen molecule is sigma 1s2, sigma star 1s2, sigma 2s2, sigma star 2s2, sigma 2pz2, pi 2px2, pi 2py2, pi star 2px1, pi star 2py1, which can also be written as kk sigma 2s2, sigma star 2s2, sigma 2pz2, pi 2px2, pi 2py2, pi star 2px1, pi star 2py1. The electronic configuration of oxygen molecule is such that there are 10 electrons in the bonding molecular orbitals and 6 in the anti-bonding molecular orbitals. Thus, the bond order of oxygen can be calculated as half of 10 minus 6, which is equal to 2. Hence, the oxygen atoms in oxygen molecule are held by a double bond. It has been proved experimentally that it is paramagnetic in nature. This is due to the presence of 2 unpaired electrons in its molecular orbitals. Similarly, the electronic configurations of other homonuclear molecules such as boron, nitrogen, fluorine and neon are shown here, from which bond order and magnetic property can be calculated, as given in this table. When hydrogen forms a covalent bond with highly electronegative elements such as nitrogen, oxygen and fluorine, the shared pair of electrons is attracted more towards the electronegative atom. Due to this, hydrogen gains a fractional positive charge, while the more electronegative atom gains a partial negative charge, making the bond polar covalent. When a number of molecules of these compounds are present together, the partial positively charged hydrogen atom of one molecule is attracted to the partial negatively charged electronegative atom of another molecule. This weak electrostatic forces of attraction is called a hydrogen bond, which is weaker than a covalent bond. Hydrogen bonds affect the structure and properties of a compound. The strength of hydrogen bonds varies based on the physical state of the compound. For example, in water, each molecule can form 4 hydrogen bonds, giving its viscosity and high boiling point. In ice, the hydrogen bonds create an open, hexagonal lattice crystal structure, reducing the density of ice compared to water at the same temperature. This is why ice floats on water. Hydrogen bond is strongest when the compound is in the solid state, and weakest or absent when it is in the gaseous state. For example, in H2O, the strength of hydrogen bond is more in ice, relatively less in water, and is not observed in steam. The hydrogen bond present in water is said to be an intermolecular bond, which means that the hydrogen bond is formed between 2 different molecules of the same or different compounds. However, in certain compounds like orthonitrophenol, a hydrogen bond is formed between the hydrogen atom of hydroxyl group and highly electronegative atom, that is oxygen of nitro group, present within the same molecule. Such a bond is called an intramolecular hydrogen bond. Thus, we can conclude that a hydrogen bond is the weak electrostatic attractive force between the hydrogen atom and the highly electronegative atom of either the same or different molecule.